Thank you for inviting me to speak today. I will cover the use of BERT for forecasting of CVE categories based on CPE. But before we get started, I would like to introduce myself. My organization is the St. Petersburg
вопросов информационной безопасности и работаю в лаборатории проблем компьютерной безопасности.
institution, namely St. Petersburg Federal Research Center of the Russian Academy of Sciences. I've been in the science sphere for over 9 years. After completing my PhD in Russia and abroad, I started teaching at universities and became project lead at our lab. This is a brief plan of a presentation. We'll start with a larger task. We'll talk about network security overall and the way it interconnects with vulnerabilities. Forecasting vulnerabilities as they are is not feasible because there are over 200,000 categories, but we can forecast them without losing data that it is important. Then we can proceed with a specific task of forecasting vulnerabilities. I will showcase which tools we used, the results we achieved, and we'll then proceed with a discussion. There are some still open challenges that need to be discussed. Without further ado, let's get started. Network security. I would like to focus your attention to a subset of network security, that is building attack graphs, analyzing attack vectors. That is about everything that deals with vulnerability analysis. An important concept to understand about vulnerabilities. It needs to be a comprehensive solution. We cannot take one single solution applied to all systems. There are a variety of network-based systems. They operate using various data transmission protocols. This slide illustrates a segment of railways. This is what it may look like for railways. When building attack graphs, our job is to identify instances that can be identified as vertices of this graph. In this way, we'll be able to provide some analytics. We can analyze protected systems, we can find bottlenecks, we can assess the criticality of vulnerabilities and build a response plan. Some are more critical, which is urgent. Other devices are less important, they can wait. Another task is about attack vectors. We analyze specific attack vectors to be used by the attacker. Which attack vectors are the most significant one? It's not a trivial task. There is a limit on the analysis depth and entry point. As part of this presentation, I will talk about the classical CVEs. There is an entire international program where a number of organizations make their contributions. They identify these vulnerabilities, put them into a single catalog. Every single vulnerability has a unique identifier, its description, and metrics. As a database, I will refer to the American NVD, National Vulnerability Database. It's one of the most popular ones, one of the most complete ones for this purpose. There must be more of them because they identify vulnerabilities on a daily basis. But last time we checked, it contained over 200K vulnerabilities, and this number is growing day by day. When we refer to vulnerabilities, it's important to understand how dangerous this vulnerability is, whether it is critical. How can attackers possibly exploit these vulnerabilities? What will it result in? We tried to analyze this through vulnerability metrics. One of the most popular standards is CVSS, Common Vulnerability Scoring System. As part of this presentation, I will refer to V2 and V3 of this standard. The fourth version, version 4, was announced recently, but as of the time I checked for the last time, there was not a single vulnerability that had version 4 metrics, which were available. And finally, how do we make a conclusion that a given device is vulnerable to a specific CVE? What comes to the fore is configurations. It is a structured language of software applications running on your device. And CPE, Common Platform Enumeration, is the most popular standard. In the middle, below, you see CPE URI, Unified Resource Identifier. These are fixed fields, they never change. The key ones are part, vendor, product, version, update, edition, etc. We can say Windows 11, Microsoft Subversion. This is to find out which vulnerability it correlates with. As you can see in the screenshot, it looks like this. You can download some JSON files from this database. These are logic expressions that put together a set of CPE URIs for a given situation, which may occur or may not occur in the system. If we have identified a certain fact, there is a vulnerability. In some cases, we need multiple occurrences overlapping for it to become a vulnerability. So this is the definition of vulnerabilities and configurations. What is left out is categorizing vulnerabilities to start to be able to forecast them. The first thing we did to solve this problem, we tried to identify metrics from various CVSS standard versions. These are the most important ones to forecast vulnerabilities, or rather to analyze attack paths. This is what we want to know, the preconditions and the results, the outcomes of vulnerability exploitation. Preconditions. We identify the ways attackers are supposed to connect to our systems and which privileges attackers require to be able to successfully exploit this vulnerability. Whether they need to be an unregistered user or whether they require some level of privileges. Outcomes. We wonder whether after exploiting this vulnerability, the attacker was able to increase their level of privileges. Confidentiality, integrity, availability, etc. This is the scope of the impact. This slide lists a number of key metrics. It's only contained in one version of the CVSS standard. While working on that survey, we can only work on metrics contained in both versions of this standard, and this is around 1/3 of the overall number. We came up a certain coding pattern for simpler representation. The system is pretty simple. It starts with C as category. C stands for category, then XXX. First, the privileges required to exploit a vulnerability, then obtained privileges after successful exploitation. One stands for having no privileges, then two will stand for being a user and three for being administrator. And the final point, final character stands for an access vector, whether it's physical, local, adjacent network, or network. Next step, we have vulnerability categories. We understand that on a given host machine, the attacker might have various privileges, and there are multiple ways for them to connect to it. So we can break this down into various states the attacker is at. And we end up having a total of 12 states, from S1 to S12.
Злоумышленник получил права администратора. И если мы
We can tell whether our device has been compromised, whether the attacker has become an admin.
с этого слайда, то мы получаем такие вот
If we build the compromising graphs, they will look like this. From requesting access to obtaining access,
но эксплуатируем уязвимость не для повышения
there are
привилегий, а
some
для
standing
ущерба. Ну, допустим, мы уже
edges,
получили некоторые
connections.
привилегии и просто
For example, we got the required privilege level, and we want to pull and steal some data from the system. This is something we can work on already, but looks like something is missing. Therefore, our next step is let's let the attacker move from one attack vector to another. Having physical access to the system, what opportunities will the attacker get? When they get the user privileges or admin privileges, all these situations are reflected in the slides as additional connections. This puts together the 4 previous graphs. This is how attackers can move across the device to get to one of the 4 states, which indicate that the device has been compromised. We have all the required components. Let's run an experiment, and let's take a look at what we forecasted and what we ended up having. Our hypothesis is this. We have a set of devices with the same vulnerabilities. Since they share vulnerabilities, they have a common configuration element that leads to shared vulnerabilities. We suppose that vulnerabilities which are grouped into the same categories, they may have the same properties. Their configuration elements might be similar. This is not a verified fact, but it is a mere hypothesis we'd like to put to a test. Based on this hypothesis, we built our experiment pipeline. You can see it in the slide. We started with building a local database, building local datasets. These datasets were tested on first basic versions of the model, then we selected the best ones. We started optimizing these parameters, and we got the final solution, and then analyzed its performance to forecast the vulnerability. So it's a pretty extensive experimental process, and we'll try to describe now. Speaking of our datasets, what is our approach to this objective? We built a total of 3 datasets for each metric, C of CVSS, which relates to a specific vulnerability category. So we trained 3 models on the same dataset, so they can actually learn to forecast a metric that generates these categories. You can see the data distribution across these datasets. The data is not quite balanced. The network access prevails over the physical access vector because such vulnerabilities are not well represented in the database. There are few of them, but similarly, one can observe that when one gets admin privileges, such cases are much more rare than others. Another point is this. Since we used with vulnerability categories, the same category might have different vulnerabilities. These different vulnerabilities may belong to different categories. So we have a multi-label classification task, where one configuration might correspond to various access vectors on the dataset level. And this slide highlights how many multi-label cases we have in this situation. There are some examples from the CSV files. The CPE were pre-processed. We removed colons and asterisks, which stands for any data version. And these lines were fed to the models as input data. And the final step, before proceeding with the experiment phase, the choice of models is this. There are a variety of models out there natural language processing is a pretty popular task, but transformers perform best for short texts. Therefore, we tried to use BERT, bidirectional encoder representations from transformers, and its popular versions. We chose BERT, Roberta, XLM Roberta, and the BERTA v3.
Собственно, переходим к результатам экспериментов.
We proceed with the experiment results. First, the first thing for us to do was this. We took the basic versions of the model, and the parameters are now listed in this slide.
Базовое тестирование. При этом
we started some basic testing.
Может возникнуть ситуация, что просто какой-то
In this regard, we
с тем куском данных, который
were afraid that one model will get lucky with the data set it gets. Therefore,
делали случайным образом между тестовой и
we randomized the data distribution every single time between the test sampling and the actual sampling. We ran this 10 times. We collected the results per metric for each experiment. Then we calculated the average, and when we calculated the average deviation.
Оказался интереснее всего. Также можно заметить, что есть
This is the value of the mean squared deviation, mean root square deviation, and the classical BERT proved
но было ожидание, что как раз
to be more impressive.
поможет улучшить модель.
We expected that the optimization of hyperparameters would help us achieve higher results.
Если какие-то альтернативные модификации
Additionally,
работают похуже
if there are some
в плане быстродействия,
BERT modifications which perform slower, if there is significant difference, we measured their velocity and performance, but we never identified any significant difference. So for batch of data, it was a matter of milliseconds. So we decided that we proceed with classic experiments with the classical BERT. We took the BERT. It goes to the Optuna framework as input data. In this slide, you can see the parameters and the steps. Below, you can see the optimal values. These are broken down into 3 lines per each metric, because for each metric, for each data set, we trained a separate model. And finally, this is the CVSS forecast results. We have the overall accuracy for all. The left-hand side value, the higher value, is after optimization. Along with that, it is prior to optimization from the previous slide. But I thought that would be best to put them together and compare them. Each access vector for each metric for each required type of privilege and the privilege obtained, we have specific values. We can see some correlation between the number of copies we had in the data set and the way the metric values decline. There is one exception relating to a physical access. No, actually, it's all pretty much in line with that. That's good. Next step. The next step is to find a way to assess the quality of vulnerability forecasting. We have 3 different models. As input data, there is a CPE URI line, there is this string, its name, product version, etc. In this case, it was GitLab, and the respective example is for GitLab. These are actual values. This is not random data. Each model, for each possible random value, it can yield output a certain value, ranging from 0 to 1. Whether a given string, text string, may be associated with vulnerabilities. Our task is to use some threshold values you see in the slide. These are identified in the slide as cat_thr, max_thr. As an output, we list certain vulnerability categories. We have a total of 3 of them as output data. This is a situation with privilege required. All of them are higher than 0.8. All the 3 of them work. In terms of access factor and privileges obtained, so 1 multiplied by 3 by 1, you get a total of 3 categories. When assessing the qualities, we broke the results down into correct forecasts, useful forecasts, and false incorrect forecasts. The correct forecast is a full match of what we expected to get and what we got. Useful forecasts are situations where we got something out of what we were supposed to get, but not in full. At the same time, we got nothing, which is superfluous. Why do we proceed this way? Because we're still forecasting the vulnerabilities of a given device. We're not forecasting all of them, but at least something which is there. While all other forecasts, we consider them to be incorrect, false ones. If we add at least something which is superfluous, it is a mistake, it's an error, because we are coming closer to a wrong conclusion. So we suspect vulnerabilities that are not there. These are our results that we got. We took these threshold values. One represents the acceptable divergence, which metric value is acceptable for building the list of categories. Second, for instance, our forecast contains nothing which is higher than the cat underscore threshold. To forecast some vulnerabilities, we take the maximum out of what we have forecast, and then we pick the closest values for vulnerabilities. We took these threshold values, we put them down, we identified the acceptable ranges from 0.65 for cat threshold to 0.99 for max threshold. It ranges from 0 to 0.5, 0.05, and the step is 0.01. We ran a variety of options, and we sorted them by the reduction in false positives and the increase in correct forecasts and useful forecasts. The most interesting ones, we selected 0.8 for cat threshold and 0.02 for max threshold, because it gives a certain degree of volatility for the decision making. The results at the same time are pretty interesting. So the overall accuracy of forecasting vulnerability categories is almost 0.87. Why we almost have 0.85% of useful vulnerabilities? So it's about 85% of us telling you something which is useful. These are the results we got. The next question is, what needs to be done next? And the first thing I would like to talk about is how to apply this in practice. To get started, I would like to start with this graph. It is the same graph of devices I mentioned before when I spoke about vulnerability categories. Some connections are highlighted in different colors. The transitions in orange, in orange, which is yellower, these are S6 to S10 and S4 to S8. These were based on the classical approach. So we analyzed the configuration as the vulnerability scanner does, so we extracted specific vulnerabilities. We know that on this device, one can exploit such vulnerabilities, but what is missing, the transition from S8 to S6, that could lead to a successful chain of attack on a given device. Forecasting could help us. Probably we're missing out something. Probably there are some devices which are not included in open databases, but they might be similar to other devices already contained in the database. But this configuration similarity, which can be identified by AI, could help us forecast that this device can be potentially compromised. And speaking of the device level, this can be a large graph level where we are missing an edge, a connection from one device to another. This is for us to get to some core assets. So forecasting could be helpful in this regard.
Они приведены на слайде, я их еще раз проговорю.
The example is here in this slide. Let me cover them again. So we have a certain operation system. And we know that in some versions, some vulnerabilities were not fixed. Then a new version is released, which does not change its architecture. We may expect that it has inherited the same problems, and we need to take that into account. We have lots of IoT devices. They appear quite often. Their vendors come and go, they get updates or not. It's very difficult to keep track of all of these, of this variety out there.
Для каких-то из устройств интернета вещей уязвимости описаны в открытых базах данных, но для большинства из них это
vulnerabilities for some IoT devices are described in open databases, but the bulk of them contain no description whatsoever. These devices have not been checked, have not been tested in any way. We'd like to make some
возможно, это устройство тоже уязвимо, оно похоже вот на другое устройство, другого
actually,
но используют там те же железки, и, скорее всего, так и будет. Здесь мы тоже могли бы что-то предположить. И с одной
there's a few assumptions we can make for a given hardware manufacturer. We assume that all forecasts, any forecast may be incorrect. Even if we have an accuracy of 85%, it's not that good. On the other hand, that's another fact that leads us to apply analytics. Probably we should look for vulnerabilities on these devices. As we carry on with problems, what did we face and why did we fail to get any results following optimization? The data is highly imbalanced. When breaking down vulnerabilities into categories, it was a theoretical assumption. These are the metric values, and the aggregated list contains 24 categories. If we look at them in reality, some vulnerability categories are not represented. They are highlighted in orange, where the true parameter is equal to 0. They will appear over time when experts add these vulnerability data to the database. They will add some values for these metrics. They will appear then one day. But for our database, they were not there. There was a certain lack of data. On the other hand, some vulnerabilities are represented across categories, but the data is insufficient. It is highlighted in yellow. For some, it is equal to 6, 8, 23, or 32. But that is not significant. Seeing this problem, we tried to operate various approaches to oversampling and undersampling at the same time, trying not to violate the nature of data. There are very few really significant vulnerabilities. There are vulnerabilities which do not cause critical damage. These are much more numerous. If we violate this nature of data, probably we will be dealing with the wrong task. But one way or another, either oversampling or undersampling failed to help to find a solution. This is how it goes, though. Next point. It is associated with the previous problem. Models get retrained very quickly. That was Epoch 4. After Epoch 4, the gap after Epoch 4, the gap between training and testing becomes unacceptably huge. The gap keeps increasing. So it was no point in retraining. So it led to some real-life overfitting. This is something we didn't want to deal with. It is slower for one type of metrics, and it is faster for others. This applies to the data set for now, and the next slide is dedicated to our plans of solving this problem in the future. Let me highlight what this diagram means. CVSS v2 and CVSS v3, these are different standards of CVSS. This is the number of vulnerabilities contained in the National Vulnerability Database, NVD, as of the last time I checked, which have metrics with such a version. In parentheses, we see the number of vulnerabilities which contain metrics with this specific version. It is 73K. They have no CVSS v3 metrics, and it is equal to 43K for v3. They lack CVSS v2 metrics. When dealing with this database, we could only work with 106K vulnerabilities, but we would rather work with a total of 237K metrics. NVD has some data gaps. It is not complete.
Которые, по сути, будут мапить одни метрики уязвимости на другие с достаточно высоким качеством, чтобы мы эти пустые значения могли заполнить. У нас уже есть результаты экспериментов предварительных, мы сейчас эти эксперименты улучшаем.
We are enhancing these experiments, but that's not the topic of my today's presentation. As soon as we expand the data set, we'll repeat these experiments, and we hope we'll get much more interesting results from them. I'm done so far. Please read this QR code. It leads to my Telegram channel. If you're interested about this, if you would like to cooperate with me, please send me a message. It was very nice for me to speak to you here. I'd be happy to take your questions, and thank you. Thank you all. Thanks again for joining us here with this presentation of yours. Ladies and gents, the Telegram bot has an option to send questions. We'll send you this QR soon so that you come up with questions and you torture him with questions, as many as possible. But now we have questions already for you. I remind you, but we start with this CVE. Normally it starts with the hardware vulnerabilities. Have you ever tried to evaluate those hardware-related vulnerabilities that are not relevant for other backends and for other devices? In this research, we did not split the vulnerabilities by different types of devices. We did have a very small set of data, so we did not have to make a sub-extraction out of it. If we had done it, we might have ended with more interesting results. Thanks very much for hitting me with this idea. We didn't do that, but I think we should give it a try and see what happens. Which kind of hardware did you use for your experiments? We did use PC for these experiments. Nothing special, really. 2 gigs of RAM, DDR5, 13x90 NVIDIA video card, not even the ATI, an SSD drive. We conducted those experiments for a long time just because of that configuration, so we could have ended with the quicker results had we had a cluster. But, you know, we are scientists, therefore we had to use the hardware we had available. Why not LLM? Why not LLM? It's a question I ask everyone here. I understand why not? Why not? Because it's 3090, not even ATI video card. You see, you could squeeze in the small LLM system there. But the fine-tuning option was key for me there, so that we could train an extra layer for that. If we could take a separate LLM pre-trained for that purpose. We used the pre-trained BERT for these experiments, and then we fine-tuned that for these experiments. It could have allowed us to find what it would be better, BERT or something else. I think in the LLM, we could have set it with the prompt and fine-tune it and use LOR for that. There are some restrictions, of course. If we use the state-of-the-art solutions, of course, they are all not free of charge, so that limits our field for experiment. But it would be interesting to try this. What are hyperparameters turned out to be the most critical for improving the precision of prediction? Maybe you can single out some features. What are the insights that you can pull out from the trained model rather than actually use it? As far as insights are concerned, we didn't have it on the slide, but it's always interesting to take a look at error metrics. What is confused with what, for example, whether we confuse physical access with local access, or local access looks like network access, and that's why we have false there, whether the configuration level of the model sees the difference between the user and other. We have some insights. It's all about that confusion that we did see there. But unfortunately, we're not certain that we can use them directly. We may have analyzed the set of data and see if the problems remain, and then we would have provided the physical and local access as the CVSS version 2. Will we be able to see these insights later on, and where? Interesting question. By the way, can I go back to my slides? No, not anymore. It's a shame. There was a slide with the reference links to the publications in some science magazines. That's where you can see the details about this particular presentation and about that one that's related to the categories. I think this presentation of yours will be published later on. You'll pick it up, take it, and you track the publishers to get more insight. I think people address you here and find more information here on the side. It's a question about the attributes. Have you ever tackled regularization and this prediction of this software, but in a different version? Could be related that it's a different version of the same software. Is there any correlation? As far as the attributes, we would give it to BERT. It transfers the text to the vectors representation depending on how it was taught. So we did not influence the attributes. If you remember that slide with sets of data as attributes, we had just that string. One element of configuration was described, and then that BERT with 192 made those vectors, predictions. As far as different versions are concerned, of course, to resolve that, we'd feed this data and saw what could happen, but another problem would emerge. In different versions of the libraries in Python, which helped us come up with a pipeline, we ended up with different results, training the same BERT, with different versions of BERT as well. So you need to go easy on that. But we mentioned all that in publications so that we can reproduce this experiment. Otherwise, it would have been much more difficult. You mentioned the absence of balance between the classes. For example, you said there are methods of like synthetic methods. You can add synthetic data to add more balance, add weights to the classes. Could you please tell us about that? I partially tackled that question of yours as a part of the discussion. Oversampling, undersampling. But we could not really see a significant change in the metrics. in terms of the improving of the efficiency of the model. I therefore did not show it in my slides. It was a failed experiment. We toyed with the weights, as you said, but we didn't have any significant result out of that either. So we tried and it didn't work out. That's the story. Okay, excellent. We'll see more breakthrough solutions from you. Okay, let's continue this question from the floor. This person is asking about more relevant cases where it can be applied to evaluate the cyber security risks. By analyzing the graphs of attacks, we see that we have new paths for intruders. You can come up with better analytics. In terms of theory, I think if our impact analysis will be more precise, if our forecast will be more precise, we may want to send this information to our pen test pals. We assume that this device may have such and such vulnerability. We, of course, may inform them in a more abstract way so that they need to escalate the privileges. So maybe they'll detect the vulnerability on the device and thus eradicate them. What about local CVC and making it local physical in version 3? They actually have something similar. When we started having CVSS v3, they started appointing physical and local. As far as CVSS v2, only local was available. As I see, CVSS v2 had them all, not CVSS v3. So we need to change CVSS v3 metrics and separate them into physical and local ones. So it's more likely that those metrics that I showed for the efficiency metrics may have looked much more interesting, but we didn't tackle that so far. One final question, we don't have much time. How did you process the NVD records with a few CVSS parameters? We are much more happy with the situation when there is a vulnerability in the version 2 and the version 3. We worked with them because it was important for us that we have one metric which only contains in the second version, and there's only one metric in version 3. At the local database, when we stored this information, we separated that there are separate vulnerabilities with the metrics, and there are separate versions of such and such vulnerabilities in version 3. So we kept on sticking to a particular version, as it were. One final question, try to give a very precise answer. Accuracy very much provides many errors when the classes are unbalanced. So therefore, have you tested other metrics as well? So so have you tested other metrics as well? To put it simply, we measured that, it was shown on the slides. We didn't test other ones, but we showed metrics for each and every category so that we could see precision recalls and the number of issues in the experiment. The balance accuracy would be a very nice thing to work with. Excellent. Thank you very much for your presentation. Let's applaud to